over just a few of these problems so that you've got to start off on these, but you're going to do these on your own for homework tonight. Let's take a look at F here. When you take a limit of a function like this, always start by plugging in. So if I go 1 over 5 minus 5, 1 over 5 minus 1 over 5, this is going to turn into 1 over 5 minus 1 over 5 is 0. 5 minus 5 is 0, and you get 0 over 0. Now, 0 over 0, be suspicious. Did I actually spell that right? Amazing. I'm not the world's best speller. So if you get 0 over 0, maybe that tells me things might cancel out. So taking a look at this one, it does, but it's a little subtle. So let's say I have the limit as y approaches 5, 1 over y minus 5. Now I need to get a common denominator here of 5 and y. So this is going to be 5 minus y over 5y. Do these cancel out? Not quite. They're close. So let's say I have x minus 2, and I have 2 minus x. Are they the same thing? No, they're very different. If you put in a 4, you're going to get 2 here. You're going to get negative 2 here. But that's interesting. I put a 4 in here. I get 2. I get a negative 2. What if I took the opposite of that? Would it work? Yeah. So what's the opposite of 2? Negative 2. What's the opposite of x? X. So now are these two equal? They are. So if you switch them, switch the order, and take the opposite, you can say those are equal. So that's what I'm going to do here. I'm going to take the limit, y minus 5, or y approaches 5, 1 over y minus 5. And it's going to be the opposite of y minus 5 over 5y. Why is that a good idea? Because now they cancel out. And so the limit, y approaches 5, of negative 1 over 5y is going to be negative 1 over 25. That's the y value it's going to approach, not 0 over 0. So is 0 over 0, when you see it in the future, do you just write negative 1 over 25? So when people ask me, what's 0 over 0, if you ask Siri what 0 over 0 is, she'll give you this convoluted answer that really doesn't make sense. I just say 0 over 0 is equal to 6 in some cases. It's equal to 52 in others. So limits are so much fun. And then, of course, we have to get to the infinite limits. Infinite limits are the idea that if you get huge, 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 will this ever settle down? So take a look at this first one. The limit as x approaches infinity of x plus 3 over x plus 5. So if you have 103 over 105 or 1,003 over 1,005, is this 3 and 5 going to make much difference? No, it's really going to be 1,000 over 1,000 or a billion over a billion, which is essentially what? 1. Yeah. So that's what that infinite limit's going to be. How about this one here? The limit of 4 times a million squared minus 5 times a million plus 1 over 1 times a million squared plus a million plus 1. Do these 5 millions and the 1 and the million and 1, do these do much? They really don't. The only part that matters is the coefficient of the biggest exponent of x. So in this case, it's just going to be 4 over 1, or 4. Now, sometimes they're not quite that simple, like C and D, but I'll let you think about those and we can talk about them. I have lots of methods of doing this. Let me just show you real quickly. Limit question, Kurt? Are you sure?
Yeah, it's from the page before.
Okay. So if you take the limit as x approaches infinity of x squared plus 3x over 5x minus 1. Do you know what that is? It is infinity, yeah. And how do you remember how to do that? Look for an asymptote? Fantastic. Have you ever heard of the Jonathan, what's his last name? It's been so long. I call it Jonathan's theorem. He had this idea that just blew me away. It was an HL2 class like this. And he said, why don't you do this? No, it was on his pre-calc. He said, why don't you match this x squared, the biggest exponent, and how many x squareds are there? 0 of them. Drop that in there. And just do that greatest exponent thing we did before. So this is 1 times x squared, and this is 0, which is going to be undefined or infinity. But isn't that great? That is so great. Watch how it works the other way. Limit as x approaches infinity of 5x cubed over 4x to the 4th plus 3. Okay? Match the greatest exponent of x. So in this case, the greatest exponent of x is x to the 4th. Match it on the top. How many are there? 0. So using that method of the coefficients of the greatest exponent of x is just going to be 0 over 4. But what's that? It's not infinity. What is it? That's 0. Don't you like that? Yeah, it's so easy. Now another quick way of showing these limits to infinity, and I want to show you this because this is how I do it in a pinch. Okay, let's say you have this one. What's the greatest exponent of x? X squared. So if you divide everything by x squared, is that a legal algebra move? It's like multiplying by 1, right? Yeah. So this is the same as the limit as x approaches infinity. 2x squared over x squared is 2. 5x over x squared is 5 over x. 3x squared over x squared is 3. 2x over x squared is 2 over x. And 5 over x squared is 5 over x squared. What happens if you have 5 donuts and you divide it amongst an infinite number of people? How much are they going to get? Essentially no donuts. What if it's 5 donuts divided by an infinite number of people squared? Still no donuts. So I would call this what? 0. This and this 0. So you're just left with 2 over 3. A fail-safe way of analyzing infinite limits for polynomials. And then this, just looking at the coefficients is the other way, but this will work every time for every situation. Okay, so do you believe me that that's true? Yes. Then prove it. Okay, go back to, and I got to format this so it's normal zoom. Come on, normal zoom. There you go. So there's a branch of calculus dealing with tolerances, and the subway got into trouble a few years back because somebody actually measured the footlongs throughout the country, and they are all about an inch short. And so he figured out that that's 1/12 of the cost of a Subway sandwich. He was getting ripped off, and so he added that up over the number of times he had Subway sandwiches, and he came up with, I think it was $1,200 or something like that. And he sued Subway, and he won, but the idea is that what happens to bread when you heat it up? Shrinks a little bit. So, they weren't being completely unfair, but most of the Subway sandwiches, were not larger than 12. They're always shorter than 12, and so that was his big gripe. So that's kind of what we're going to do with a proof. And when we do formal proof, what we're looking at are what we call tolerances. The spread of this, spread of that, spread of x, spread of y. And if we have a relationship between the spread of x and the spread of y, we can prove that the infinite limit exists. And don't worry about this. We're going to hit this again tomorrow, but I'm going to do it right now on video real quick. Is the value for x that you're off is called delta. The value of y that you're off is called epsilon. And you can barely see it, but this is that big funny E here. L is the limit. Limits are? There you go. So to prove, all you have to do is show a relationship between x and epsilon. And when you do that, if when x gets bigger, 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 and epsilon gets smaller, 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 it has to do one thing, and that is end up at that limit. So with these two things, we're going to be able to prove that a limit exists. So in this one, u of x equals 3x over that. What's the limit as x approaches infinity of, I'm going to call it f of x here, not u of x. What's that limit going to be? Very good, 3/2. So if you take the absolute value of f of x minus L, that is the difference between the y value and the limit. It should be less than epsilon, and we're going to prove that tomorrow.